So this was a brief overview of today's lecture. Now let's talk about the topics that we covered in the last lecture. We were talking about the applications of linked lists, and we saw that there are different types of data types that could be in a list. And the question was, how could you convert that or keep that in a linked list? So this was one possible structure. I'm not saying that this is how it's actually implemented in Python, for example, but this is one possible structure that you could adopt. I'm not saying that any specific language actually adopts this, but this is one possible structure. Okay, it has its pros and cons. So if I were to take a few minutes and ask you, what are the pros and cons of having this list, which has different data types in this data structure? What are the pros and cons? Okay, would anybody like to talk about that?
Sir Shanir.
Jishan.
Sir, if we have different data types in one list, then we can't specify how much space to reserve for each element. And one advantage would be that we could have different data types in one collection as a record, somewhat of a record.
Yeah, so basically this has allowed you to keep different data types inside a single structure. And if you were to do that in an array, you would probably have difficulty, especially in terms of efficiency, all those issues that we've already covered. What this gives you the advantage is that, for example, if you were to, instead of making the second element high and you wanted to have a much longer word over here, it wouldn't require any change in the data structure. All it would do is it would make this pointer, and perhaps if the space around this is already utilized, it would create another memory block which was longer. For example, you had hello over here, and you would allocate another space in memory, and you would simply change this pointer to now point to the new memory. Okay, and this block would be collected by the garbage collector. So that's one clear advantage. Another advantage is that as you are changing the data type, so for example, instead of having an integer over here, you wanted to create some kind of a float over here, which is taking up more space, then you could reallocate this node, okay? And this pointer would change to a new node, and this pointer at the end of the node would continue pointing to the remaining elements, okay? So you can see that this has a lot of flexibility, and especially in terms of space storage, this is very efficient, okay? So then we saw that you could have linked lists within a list, and you could have one list over here and another list, which was the original list. The new list has a variable L2. The first list has a variable L1. And but if you wanted to have L1 as part of L2, all you had to do was have a list, a variable defined as list, and the system would know, the computer would know, essentially that after the term list, you would actually have a pointer, okay? Just like you had a pointer after the string type, okay? So this pointer over here would point to the entire list, which was being embedded over here. And then the next pointer would go to the next element in the list, L2. So notice that L2 only has 3 elements in it: 20, a list, basically an integer, a list, and a string. Okay, so the first, second, and third. The second is itself a pointer to another list. Okay. And then we looked at the Python data structure, and we saw that in Python you could actually have what are called dictionaries, which is perhaps the closest that you can think of as getting to a linked list. So a dictionary can be thought of as one of these nodes. Okay, so here what we're showing here is a node which comprises of different data types. So it has a name. It's basically got all information regarding, for example, a person, a contact in your contacts list, and each of these elements within this node has got a key and a value. So key, for example, is a name. The value is Ahmad here. The key is element. The value is the date of birth, and so on. Okay. So we went over the Python dictionary structure. And then we said, well, if you wanted to create a linked list of employees, okay, or this could be a linked list of all your contacts in your database, then how could you use this Python dictionary to be able to create that? And here, this was an example of how it could be done. So again, this is a hypothetical situation. This is not, I'm not saying that this is actually how it's done in Python, but this is how it could be done. You could have a variable called employees, and it could be pointing to a linked list. Okay, so this linked list here, I'm showing you a slightly different architecture. It's separating out the nodes, the actual data, from the actual pointers of the linked list. So the linked list only has two elements, the pointer to the node and a subsequent pointer to the next element. Okay, so it's a different architecture. The node itself consists of this entire dictionary of Python. All right. So this was what we covered last time. Then we looked at applications of linked lists. So here we saw that the Fibonacci sequence, which was there in the first homework assignment, could be implemented using a recursive function. And here it's a recursion. And I'm going to look at the homework number 2 recursion. And we'll see how that compares with the recursion, with this recursion, and how I also, as part of homework number 2, I asked you what is the time and space complexity of that particular the search function. So notice that here we said that the space complexity is getting it. I haven't shown you what the complexity actually is, but it is implemented as a stack. In other words, the space is going up. It's not a constant. So as you go for larger and larger Fibonacci numbers, this space amount could become extremely large. Okay, and why is it becoming extremely large? Because it's going to be stored as a stack. Okay, and not only as a simple stack, but actually as a binary stack. So in other words, when you call Fibonacci of 4, it's going to not only save this, but it's going to space in memory space for Fibonacci of 3 and Fibonacci of 2. Okay, and this again is going to spread out. So Fibonacci of 3 again is going to have 2 sub branches and so on. Okay, so again, so Fibonacci of 100, you can imagine that it would become an extremely large amount of space that would be required. So this was a binary tree implementation of the Fibonacci sequence. And we looked at a linked list implementation of this. And we saw that you could have, for example, up to 4 pointers, a left pointer, a right pointer, and also a parent pointer. Okay, so that if you're working on this portion of the algorithm and you're calculating Fibonacci of 3, once you're done with this, you know where that you're supposed to go up the stack. Okay, so you wouldn't lose sight of, because here in this case the stack was linear, it was easy for you to go down the stack. But if the stack itself is bifurcating, then you need to store it as a linked list, and then you need to be able to go not only down the stack, but you also need to go up the stack. And whenever you need to go up the stack, you need to have a parent pointer. Okay. And then we look at something called the binary search tree. And here, basically, the interesting thing was that in the early part of the course, we had mentioned that you can store data. You can assume that data is sorted. Okay, and if you have it sorted, then it's easy to do a binary search. But we didn't really talk about how it was sorted. So here what giving you an idea as to how you can actually sort it. Um, not a post sort, but a pre sort. In other words, as data is coming to you, you already put it in a data structure which is already sorted. Okay. And so the example that we gave you over here was the following. And I went over this a little fast last time. So let me just show you how you would create a binary search tree. So for example, if you're coming up with these numbers, how would you get started? So again, let me get some feedback from you. The first thing that you'll do is you'll put down number 23, and then you'll start creating this. So this will be a single node consisting of the number 23, okay? But it also needs to have pointers, but the actual content will be the number 23. So this could sort of be like one of these nodes over here, and the data over here is the number 23, okay? Which would be an integer in this case. So where do we add number 15 now in this linked list? Can somebody tell me how we did it last time?
The left side?
Yeah, so basically the idea is that if the number 15 is less than 23, we simply have we create space in memory, okay? And we create a new node, and we have the left pointer pointing to this space, to this node, all right? And the parent pointer of this node, this will also have a parent pointer, will point to the node 23. Okay, so that's 15 is done. 96, where do we add 96? I think this should be kind of obvious. It should go to the right side because
the right side.
96 is bigger than 23. Okay, so now we're going to use the right pointer of this node to point to the memory location where this node is stored, number 96, and this will also have a parent pointer. Okay. Now, initially, the left and right pointers will be null. Okay, for all of these, left and right pointers will be null, and the parent pointer of this will also be null. Okay, but now as we add the number 72, what's going to happen? Can somebody tell me how we're going to add 72 to this linked list, to this binary search tree linked list?
The bottom right pointer, and then a new pointer that goes left.
That was left, right. So we're going to change this instead of the left, instead of the null pointer, it's going to start off by saying, is the number 72 bigger or smaller than 23? So it's going to be bigger. It's going to do one comparison over here. Then it's going to come to 96. It's going to, is number 72 bigger or smaller than 96? So it's going to be, it's smaller than 96. So it will now see, well, the left pointer is pointing to a null pointer. So what we're going to do is we're going to create another node. The contents will be number 72. And now the left and right pointer are going to be null. The parent pointer is now going to be pointing over here. Okay, so I hope that is clear. And then this continues on. Okay, so the question was, what is the time complexity? Okay, and we answered this by saying that this is order of h. Now, I didn't say this is order of n, and the reason was that when you keep on adding this, you'll see that this is an imbalanced tree. Okay, why is that? Because these numbers are not really coming in an ideal sort of way. You know, if you look at it, these numbers are between 1 to 100, and a relatively small number 23 came in the beginning. Okay, now imagine if the number 8 had come in the beginning, then it would have been completely lopsided because that's the smallest number in this entire data set. Okay, so it would have started off as 8, and then every number would have been on the right side of this. Okay, so it would have been completely lopsided. So now the question was, how much time does the search take? And earlier we had said that it takes order of log n, and we said that it's basically order of h, but that comes out to be order of log n. So the question is, what is order of h? Okay, is it always ordered the same thing as order of log n? And when would it not be order of log n?
Sir Tariq, order of H is, I think, the height of the entire binary search tree, the
Yeah.
height of the longest, the height of the longest amount of pointers in the binary search tree, and it won't be order of log n whenever the two sides of the binary tree will not be equal. Then it will be bigger than order of log n.
Exactly. So what's the worst case scenario for H? What's the worst case scenario for this?
Order of n.
Order of n. Why is that?
Because in the worst case scenario, it will be completely lopsided, which will basically mean that it will have to go through every single pointer in order to reach the end.
And in what scenario would that possibly happen?
I don't know if, for example, the first pointer is 1, then every value that comes after it will be greater than 1. So all of it will be so it will basically be a single straight line.
So that's not exactly right. Does somebody
Yeah.
else have an answer for that? Somebody else? And when would it be exactly, or when would it be order of n instead of log n? Can you give an example where that would be the case? Don't think of this example, but think of another example, some maybe 3, 4, 5 numbers where they would all be order of n.
How about if all of the numbers were either in ascending order or descending order?
Okay, good. So unfortunately, I'm not getting other people to participate, which is what I was trying to do. But Tariq is suggesting that if all of them were already ordered, okay, so for example, if you had the numbers 1, 5, 10, 20 coming in this specific order, so you would have the number 1, and then the right pointer would go to 5, and then you would say 10 is bigger than 1, 10 is bigger than 5, so you would add it over here to the right pointer. 20 is bigger than all of them, so it would continue like this, okay? So it would, each one of these would be to the right pointer, and clearly this would be completely lopsided, which would be order of n. So that's the worst case. Now, can somebody tell me why in the best case scenario, in this case where it's completely balanced, why would it be order of log n? Preferably somebody new. So best case, why would order of h be approximately equal to order of log n? Can somebody try to give me maybe an intuitive or even a mathematical
Sir
answer to
Abdurrahman
this?
here.
Ji Abdurrahman.
Sir, I think that from the it's in the middle, the values in the middle, so it is easier to reach from either side.
Okay, so think of
52.
this. Think of this, and let's try to see what's the relationship between h and n. Can somebody tell me what's the relationship between h and n? And this is a bit mathematical, but can we write an equation for n? What is n equal to? Let's say if we know h, okay? Suppose h is, in this case, it's 0, 1, 2, 3. So we're saying that h is 3 in this case. Can somebody tell me how many nodes would there be if it's perfectly balanced? Not a very difficult question. H is let's say 1. Okay, so you have 1 node and the height is 1. Okay, so how many what's the value of n? The number of nodes.
3.
Number of nodes is 3. How did you get 3? That's 1 plus 2, right? If the height becomes, instead of 1, it becomes 2, then we're assuming that's a binary tree. So how many nodes are there?
6.
7.
7, sir.
7. So can somebody tell me the equation for this?
Sir, so it's 2 to the h.
2 to the h. Is that the right answer?
So 2 power n plus 1 minus
2 to the power
n plus 1 minus 1.
n plus 1 minus n is, so we're calculating n over here. So I think what you mean is to the power h plus 1. Okay, is that right? So basically we're saying, and I think you almost got it right. So it's to the power h plus 1 minus 1. If you think about it, if h here is 1, then this is 2 to the power 2 minus 1, which is 4 minus 1, 3. Okay. In this case, when h is equal to 2, this is 2 to the power 3 minus 1, which is basically 8 minus 1, 7, and so on. Okay. So essentially what we're saying is, if n is equal to 2 to the power h plus 1 minus 1, then what's the relationship between h and n? Can we say that order of h is equal to order of log n? How would we show that? Or can we roughly say that? Any ideas?
Yes.
Yeah, go ahead.
Mathematically, you can say that because n plus 1 log n plus 1, mathematically you can say that. But I think the worst case scenario, the order will both be equivalent. Because the
Okay.
worst case scenario will be a log n, because the constant values will be removed, and the worst case scenario of h will be equivalent to log n then.
Oh, so you're saying the worst case scenario, but right now we're discussing the best case scenario. Okay, so let's just focus on the best case scenario where it's completely balanced. Okay, so all you have to do is when you want to go from here to here, then if you want to figure out the relationship between these two and you know that the answer is order of h, then all you can do is simply take logs on both sides. Okay, so you can take log of n is equal to h plus 1 times, or if we neglect this because this is essentially constant, it's log of 2. Okay, so you can see that the relationship between h and n is that of a logarithmic value. Okay, so basically h can be thought of as being proportional to log of n. Okay, I hope this is clear from this equation, that as h increases, then the number n, that there is an exponential and logarithmic relationship between those two. So once you've got that, you should be able to say that in the best case, order of h is equal to order of log n, but in the worst case, it is equal to order of n. Okay, so this is the worst case, and this is the best case scenario. Okay, and on average, actually, it's also order of log n. I don't want to go into the details of that, but on average, you can also should be able to convince yourself that's order of log n. Okay. But
Sir, why not order of one?
okay, so
Because अगर list के बीच में like in the first instance we find it,
okay,
it is possible.
so let's explore that a little bit more. Let's explore each one of the cases a little bit more. So we're talking about search, insert, and delete. So let's take a look at each one of those cases. I've already convinced you that n is proportional to the power h plus 1. And so we can see we're convinced with this case. Now let's try to figure out if these three are actually true or not. So, and in what cases will they be true? So if you're doing a search, then you can say that the worst case scenario is going to be that you have to go all the way down till the one of the leaves of this. Okay. Clearly, the search will either get you right, get you the answer immediately, or it will go down one of these paths and maybe take you all the way to the leaf. So in the best case scenario, okay, so in the best case scenario, it would be order of 1, right? Which is what I think one of you were referring to, is that what if you were searching for 52 and you got it right away, okay? In the worst case scenario, it would be order of h, okay? And h can, in some cases, be proportional to log n, depending on whether it's balanced or imbalanced. On average, it comes out to be order of log n. Okay, and I'm not going into the details of that, but you can think of the best case and the worst case as easy to understand. So search, I hope, is clear. Now, what about insert? If we look at what we did over here, we were inserting, right? And we inserted each one of these elements. So what's the best case and the worst case scenarios for an insert? How long would that take? What's the best case scenario? And how exactly would you do a insert? So for example, you are now doing insert of the number 53. So exactly how long is this actually taking you? And can you tell me that, can you go through the steps that it's going to take? Can somebody do that for me? We try to insert the number 53. So we need to find out where is it going to appear and how long is it going to take? Both, well, in terms of time complexity right now.
So it's going to take 2 steps.
Okay, tell me the steps.
Like first it will check if 57 is greater than 52. So that's true. And
Yeah,
then it will check if
53.
it's less than 53. And then it's going to check if 53 is less than 77. So it's going to place it in between.
Okay, but you've also got 65. So it's going to say as 53 is less than 77, then what is it going to do?
It's going to go down, yeah.
Yeah, so it's not just 2 steps. It's going to go to a third step. It's going to say, is 53 now less than 65 or greater than 65? So how many comparisons? First comparison, second comparison, third comparison. It's still less than 65. So it's going to make a fourth comparison. And then once it gets here, then what is it going to do? Then it's going to add 53 over here. Okay.
So is it log n plus 1?
So it's taken in this particular case, in the worst case scenario, it's taken order of h. Okay. And if you remember, when you're doing order of something, order of h plus 1 is basically the same thing as order of h. I hope you remember this from your initial equation. Right? So h plus 1 is the same as h. So this will take order of h in the worst case. Right? In the worst case. In the best case, we can see that it will take order of 1 because it could add, well, no, let me take that back. What's the best case scenario over here? I think we got a little too carried away with this. What's the best case scenario? If it's completely balanced.
Sir, what if we end up with the same number? Where will you put it then? If I
Okay,
want to
so
enter the 52.
that's a good point. So this is assuming certain things. And one of the things that I didn't mention is that it's assuming that all the numbers are non-duplicating. Okay, so it's not going to, just like in the Python dictionary, the keys have to be unique. So you're not going to add 252s, you're not going to add 261s. Okay, that's just one of the assumptions.
Okay,
Otherwise,
then I suppose then the shortest would be 1 step.
Okay, tell me that example. What's the shortest?
For example, if we get 53, we get no wait. The best case scenario.
So it's going to take it down anyway.
Yeah, it's going to take it anyway. Yeah.
So even the best case is actually not order of 1. I got that wrong. It's still order of h. Why? Because it's always going
to move down the entire height.
Yeah, it has to go down till the leaves. Okay, these are the leaves over here, and it's going to add it as a leaf. And the best case and the worst case both are order of h. Okay. And depending on how the balanced or imbalanced it is, that could be order of log n or order of n. Okay. So that's done. Insertion is done. Now, what about deletion? How are we going to do deletes? Let's take a fresh page on that. How are we going to do deletes?
So it's the same as search. It's going to be the same as search. For example, we end up with 52 to delete. So it's the first thing. So order of 1 is the best case and order of log n will be the worst case.
Okay, best case, order of H is the worst case. Is that right? Okay. So can somebody tell me what happens when you want to delete the number 52? What are you going to do? I haven't told you. So this is like you thinking. So you need to think through this process. You know what a binary search tree is, but we haven't really talked about how to do deletions. So let's put our thinking caps on and see how would it actually work. Can somebody think through this process and tell me what happens when I delete number 52 from this entire binary search tree?
I'm gonna say you can't delete the number 52.
So basically you're saying
You
you
can't
can't.
delete it.
Okay, so let's assume that
Yeah.
you can't delete it. Okay, let's take a simpler number. Okay, let's delete number 61. So how are you going to delete that?
Go down 4 steps and delete it.
Yeah, so you'll have to do a search. First of all, you do a search for the number 61. You'll end up over here. Once you've done the search, exactly how will you delete it? Well, kind of obvious. You'll make the left pointer go to null. All right, and you'll clear up this. The garbage collector will clear up 61. Okay, so far so good. We've deleted the number 61. Now, can somebody tell me how to delete the number 9? So this was a leaf. And deleting any one of the leaves is fairly straightforward because there's nothing dependent on this. How would you delete the number 9 from this list?
Sir, excuse
Sir, could you?
Sir, I wanted to ask
Please mention your name so I know who I'm speaking to. I think it's Kunoz.
I am Kunuz bin Rashid.
Yes.
Sir, I was saying that why are you taking the pointer to null? I mean, if you have removed one element, then why are you making the pointer 0?
Okay, so a good question. Can somebody answer that? Why, when we're deleting the number 61, why are we making the left pointer from 65 null? Can somebody tell me the answer for that?
Because null means that it has no value.
Null has no value. And remember, when we started off, we said, if you remember just a little while ago, when we started off with creating this tree, we said that initially what happens is that if we suppose we only have the number 23, okay? So when we add number 23, and this is the only value in this entire linked list, then the left pointer is going to be null, the right pointer is going to be null, the parent pointer is going to be null. Because basically this says that you can't go on the left or the right or the parent. This is the root, okay? So by having a left pointer being null, it basically means that there is no number which is smaller than this number. Okay, I hope that's clear.
So I have a question.
जी सोहेब.
सर अगर हम 23 ऐड करते हैं या कोई भी नंबर हम लिस्ट में ऐड करते हैं तो जो वहाँ पे पहले से नंबर्स होंगे उनको रिप्लेस करेगा या उनके साथ उसी लिस्ट में ऐड होगा?
Okay, so you see, remember, we are assuming that there are no duplicates, number one. Okay, now when we're saying that there are no duplicates, so it can't replace a number. So let's say, remember, let's do this exercise again because I think not everybody followed this. Initially, you got the number 23. This was your first contact number, and you stored it. You stored it as a single node. There's nothing else. Now along came the number 15. This is another friend of yours, and you need to store his phone number. Okay. So now we need to add the number 15. So what we're going to do is we're going to make a linked list. And since the number 15 is smaller than the number 23, the left pointer is going to point to this number 15. Okay. So we're going to add it to the left pointer. We're going to create a new node in memory, and the location is going to be pointed by the left pointer. Okay. And when we add the number 96, the right pointer is going to point to it. Okay. So I hope people are getting over the basic concept. Okay. So let's go on, and let's now try to figure out. So I hope this question is clear, that why does when you delete the 61, you will now have the left pointer pointing to null because there's nothing which is smaller than 65 in this entire linked list. Okay. meaning that there's nothing which is between 52 and 65 actually. Okay, if you think about it. So now my question was, coming back to my original question, how would you delete the number 9 from this linked list?
Sir, it's Tariq.
Ji, Tariq.
The entire branch will be deleted. So either you have to delete the entire branch, or you have to delete the number 61 from your the number 61. I think it was 61 from your data, and then reassign the other two values of the branch.
Okay, so here's the suggestion that if you want to delete this number 9, somehow you've got to take care of these two who were subordinate, who were children of this parent. Okay, it's like all of a sudden one of the parents have died, and now these children are orphans. So these orphans have to be taken care of. And now, if you think about it, here's my solution to it. You can take this number 8 and you can place it over here. Will this work? And you make this left pointer null pointer. Can somebody tell me if this will work? Will the ordered tree continue to be ordered in this case?
No, we'll have to keep 15.
Tell me why this will not be ordered. Because suppose you're searching for the number 15. You would say, is it less than 52? Yes, you go this way. Is it less than 23? You go this way. You find 8 over here. And then you'll say, is 15 greater than 8? Yes, so you go this way. So is this still ordered, or has the ordering been lost? Would you like to change your answer? Let's do another example, okay? Suppose that we're deleting the number 41, okay? My contention is that we can simply take the leaf which is underneath it, 33, and replace it over here. And my question is the tree still a binary search tree? So if you're searching for the number 47, will you get to the right place? Think about it that way.
Yeah.
Sorry?
Yes.
So I hope you'll be able to convince yourself that if you take one of these guys who have leaves under it, and if you delete it, all you have to do is take the left node and place the left node in place of the node that you're deleting. And
but that will require back pointers, right?
yes. So remember, we are using back pointers, okay, to implement this. Well, I didn't really tell you how we're implementing it, but yes, we would have to use back pointers. Okay. So another reason why you need to have back pointers over here. So take the number 96. If we delete this, then we'd simply take the number 92 and we put it over here. Okay. And hopefully you can convince yourself that it will work every time. Okay. Can somebody tell me a more difficult problem of deletion?
Sir, what if we deleted 23?
What if we deleted 23? Yeah. So that is now a more difficult problem. Okay, so let's see. I'm going to remove all of this. Okay, and now let's try to see what happens if we try to delete the number 23. So now what do we do? Any thoughts? And again, put your thinking cap on, see if you can find a solution to this. It's a tricky problem, but if somebody can do it, they definitely deserve commendation. That's all I can offer right now. So how would you delete number 23 from this? Let's use the same technique. Will this work? Take the number 9 and place it over here. But then that begs the question, what happens to the number 9?
Sir, Saad here.
Ji, Saad.
What if we just bring number 32 to the place of 23? 33 to the place of 23.
Number 33 to the place of 23. Whoa. How did you guess that?
I just thought of how It's just intuition. I don't know how to explain it, but that's
Okay,
what I-
so your intuition has is really doing good job today. So do you think that this will work? Can somebody tell me, will this continue to be a binary search tree? So what we're saying, who was that? I'm sorry, I didn't get your name.
Saad.
Saad. Okay. So Saad is suggesting that we delete the number 33 from here and we bring it in place of number 23. So can somebody tell me whether Saad is right or wrong?
So are we allowed to use any number from the tree, whether it's last or first?
So can you speak up a little bit? I wasn't able to hear you properly, sir.
So I'm asking that are we allowed to use the last number? Can we skip the one in the middle, like 41
Yeah.
or 9?
Yeah, so it's your choice. You know, basically what you say, what Saad is saying, is that you go to the towards the right link, and then somehow basically he's found a solution. I mean, let's just look at the solution. Will the solution work? Let's not look at the algorithm right now. If we put the number 33 over here, will that continue to be a binary search tree? Does it maintain the requirements? In other words, is this is if you're searching for 41, will it be still be to the right of it? If you're searching for 15, will it still be? Does it retain its integrity?
I think so, yeah.
Okay. So people are agreeing that Tariq is agreeing that it does retain its integrity. In other words, the binary search tree always has smaller numbers on the left and bigger numbers on the right of every node. Okay. You can see that 41 is bigger than 33, 9 is smaller, 47 is bigger than. So now can you convert this suggestion from Saad into an algorithm? How can you generalize that? Let's assume that now I'm not deleting this number. I'm deleting the number 52. And can somebody tell me which number should I replace over there?
Sir, Babar here, 61.
Babar. Okay, 61. And again, what's the algorithm? Can you tell me, Babar, what's the algorithm that you use? You have an algorithm now, right? No longer just intuition. You just have to spell it out. What's the algorithm? Somebody
Well,
else?
in this case, can't we use 72 as well?
Sorry?
In this case, can't we just delete 70? Can't we just place 72 in that place too? That would work too.
Okay, so let's assume that instead of placing, we took 72 and we placed it over here. Okay. So will this work? Can somebody tell me, will this continue to be a binary search tree? 72 is no longer over here. We've placed it over here. Can somebody tell me, will this still be a binary search tree?
Sir, no, because it's greater than 65.
Yeah, exactly.
Yeah.
So if you're looking for any number 65 or 61, all of those numbers, it will start searching on the left side because those numbers are smaller. Okay. So now you're getting an idea, we're getting close to an algorithm. So can now somebody tell me whether 61 would work and why would it work and what's the algorithm?
Sir,
What is it?
61 should work.
Yeah.
But I'm not sure about the algorithm.
Okay. So think about what we did over here. When somebody has a thought on it. Unfortunately, you might be in the auditorium and there's echo over there, so we can't listen to you. Okay.
Sir,
Ji.
sir, this is Amar.
Yeah,
I
Amar.
believe that it's the leftmost node on the right hand side. That's what I can think of.
Okay, super. Okay, that's exactly right. So basically what Amara said is that you go on the right side, the right link, and you find the leftmost of the right link. Kind of complicated, right? So basically you go on the right because all of these numbers are bigger, okay? And now you go to the smallest number on the right side, okay? And you take this number and you place it over here. And
Sir,
all of a
but
sudden, G. Ji, Tariq.
Sir, but Heather, if there's one pointer, it will only go to the left, right?
What do you mean by if there's only one pointer? You mean
Like in the example of 9 and 8, it was
yeah,
only one step. So
yeah.
you to go directly to the left instead of.
Yes, yes. So it's
Uh,
different from for each case. So there are three cases basically that we talked about. First is the leaf. Okay. If you're deleting a leaf, you simply go ahead and delete it and no issues. Okay. You just have to manage the pointers. If it's the parent of a leaf, then you have a different process. Then you take the left leaf and you place it over there. Okay. So deletion is kind of complicated. It's very complicated in binary search trees. But if it's in the middle, if it's not a parent, if underneath it the children are also branching nodes, then it's the most complicated case. And there what you do is you go to the right side, okay, and then from the right side you go to the leftmost case, okay, and then you find the leaf which is on the leftmost case, and you take it and you place it over here. All right. And voila,
Sir,
you'll find out
Abdurrahman,
that it'll
But
actually
sir,
work
on the
also.
case of 52, can't you use
Ji, go ahead. Case of
on the
52.
case of 52, can't you use 47 as well? Go left.
Can we use 47, go left and take the rightmost? Okay, that's an interesting thought. So let's see if that will work also. So you take this 47 over here, and instead of this, that's a good thought. So will this work? Yeah, this
Yeah,
will also work. This will
yeah,
also work.
sure, I
Very
think.
good. Okay. The standard technique that I found that is given is to go to the right and take the leftmost. I'm not 100% sure, but you can test it out whether going on the left, taking the rightmost will also work, but I think it will also work because the logic is still there. Okay. Excellent thought. So now you guys are true software computer scientists, I can see, because now you're actually thinking for yourselves and trying to come up with algorithms which may not be there in the book, but you're coming up with solutions which are making sense. Okay, great. I'm really happy with that. So let's think about a little bit slightly more complicated case. Let's say that let's go back to the earlier case that we deleted 52, took 61, put it over here, okay? And now next, suppose that now we're deleting 65 as well. Sorry, now we're deleting the number 65, okay? Now what's going to happen? There is no left pointer on 65. Now we want to delete 65.
So the right pointer will replace it like 72.
Yeah, so right pointer will replace it. So you can see that there may be a few cases, but there are broadly three cases, and the rest of them you can sort of generalize. Okay, but deletion is complicated. But now the question is, will deletion always be order of h or order of log n? So let's just focus on the order of h. Can you convince yourself that it will still be order of h?
Yeah, Heather here. Yes, sir, because we have to traverse the whole tree downwards.
Okay, very good. So so you have to traverse the entire tree downwards to be able to find the thing. So the search actually is taking order of h, and then the replacement actually is a constant. Okay, you can almost see that that by once you found the number, then you simply have to replace it over here, and then it's not really taking a lot of steps. Okay, so we've hopefully convinced ourselves to see that deletion is also order of h. Okay, so we are running out of time. So in the next 5 minutes, I'd just like to very briefly go over the homework assignment. By the way, the binary search tree implementation is very clearly a linked list, okay, with a parent pointer. This kind of obvious. And so this is the summary that we were trying to achieve. So we found the balanced binary search tree. We found out that it is superior to all the others because it's efficient. Okay, it does better than the best or as good as this. It's order of log n. So it's better than all of these. Okay, the insertion is also order of log n, which is better than all of these above, and the search is as good as the sorted array. Okay, so it's clearly the superior solution that beats all the other solutions that we had looked at earlier. There are other applications of linked list, but I think I'll skip this for right now. In the homework number 2 solutions, there are a few things that I thought I'd like to just point out. I'll give this out to you as part of the solutions that you can see, is that this was the algorithm that I had looked at. And if you can, so this is what we mean by a specific flow chart. So earlier we had said, can you do a binary flow chart where the top search the top half and searching the bottom half was sort of left as blocks. And whenever you have something like this, search the top half and search the bottom half, you can almost see that this is sort of like a recursive function because this was searching the entire list, right? And now you want to search a subset of that list, okay? And you want to repeat the whole thing again. So it sort of tells you that it should be a recursive function, okay? Now, where people got it wrong, I was looking at some solutions, is the time complexity. So, and I'll leave the solutions with you, but and if in case you didn't happen to glance at the solution, what do you think is the time complexity is very clearly order of log n, right? Because this is a binary search, but what does that assume? Does that make any assumption about how the data structure is stored? How this list is stored?
An ordered balanced list.
An ordered balanced list. Perfectly right. So in other words, it's stored as a binary search tree. Okay. Why? Because then if you're trying to search for it, this is exactly what the binary search tree will do. But if you have it sorted, if you had it saved as an array, would it work also? Would it also work if it was saved as an array?
I don't think so.
As a sorted array.
I don't think so because arrays are contiguous, right? I don't think you jump around in an array.
Well, think about it some more. It would still be binary. It would still be log n. Why is that? Because if you wanted to go to the middle, okay, so here's a solution. So here basically what we're doing is we're going to specific locations. We're setting I to be somewhere in the middle, okay? And then you want to go to this particular location. So if it is a sorted array, it is contiguous, so you should be able to jump to the middle of that array, okay? So the answer is that if it's either saved as a binary search tree, okay, or a sorted array, then in both cases, the order of log n will work. And I hope you'll be able to convince yourself to see that that is true. All right. Now let's talk about the space complexity. What is that going to be? Now, as soon as you think about recursion, you're saying to yourself, well, it has to be, it's not going to be constant, right? Because when you're going to implement this, let's say this is how I've implemented, you're going to say, well, this is search B, and now you're doing a recursion inside it. In one of those two paths, you're going to do a search. Now, can somebody tell me, is this going to be, how is the space complexity going to be? We've got a couple of minutes left before I've invited Dr. Zaheer, so quick answer for this. Can somebody think about, is it possible that, G?
Around, since it's using the same memory location, will it be O1?
Who is that? That's Rayan?
Yeah.
Okay, very good.
I actually got this wrong in the because
Okay,
I
but
thought it will be proportional to
okay,
time
but
complexity.
can you tell me why will it be order of one? Why do you
It's
why do you why will it be order of one?
because it's using the same. At least this is what I can thought of. It's using the same memory location for whenever it recurses. It
So
doesn't really.
so in the previous cases when you were doing a stack, right? And you were for example, in this particular case, remember what we were doing was we were saying that you have Fibonacci of n minus 1 and n minus 2. Okay, you're summing these two up. In this particular case, where you're doing a factorial, you're saying that we need to calculate f of 4, you need to have f4 times the factorial of 3. So you need to store the earlier values. All right. Now the question is, in this particular case, do you need to store the earlier processes? Okay. So if you're simply searching on the right side of the list, okay, you need to keep track of the earlier parts. You're just trying to see whether the answer is true or false, right? So I'm running out of time. So think about this. This will not need to store the earlier search, okay? Once you figured out that, for example, the uh, the number that you're looking for is on the right side of this list, you can actually forget about the rest of the list, and you can now simply focus on the right side of the list. If you find that this number that you're looking for is smaller, then you would simply look at a subset of the list, which is just the left portion, okay? And you can forget about this. And so you actually don't need to store the earlier processes, okay? You don't need to store the earlier search functions. So the space complexity is actually going to be order of 1. It's not going to be order of n.